Hey, everybody. Good afternoon. Please, for attendance today, answer this question in the chat. If COVID was all over with and you had $50 million, what would you do? While you're putting that in, I wanted to congratulate you on finishing 1/3 of the semester. This is week 5 of 15. So we're 1/3 of the way through. Good job. And I wanted to let you know that you have learned probably about 80% of what you need from this class for senior seminar. So we have a little bit more for you to learn in order to prepare you for senior seminar, mostly about curve fitting beyond this point. And then, yeah, you'll be completely equipped with what you need from this class for Physics 4210 here at App State, among many other things in life, but that's one of the things this class is supposed to do. Okay, so that's some good news too. You could kind of tune out the rest of the semester and still do great in senior seminar. Not that I want you to do that, but just saying, like, it may be a thing to just keep you calm, to help you chill out when needed. Do we have questions about anything? Anyone have questions? It appears we do not have questions. Okay. Then we will move on.
Actually, I have a question. It's kind of unrelated. Do you drop the lowest homework grade? Is that one of the? I could just check the syllabus, but
I would also have to check the syllabus to be sure.
Gotcha.
I don't know. But I will check and let you know next time, for sure.
All right, thank you.
Sure. Other questions? Are you asking for a reason? I think that was Brendan about the homework.
I'm just less than confident in some of my answers on this past one.
I just checked. It is dropped.
Thank you, Abdel.
Sweet. Thanks, Abdel.
Okay. So this is going to be the one you want to drop, Brendan, you think?
Maybe. In the end, that might be up to you.
Okay. Did it seem like too much? Not enough? Just right? This homework?
I thought this homework was pretty all right.
I didn't hear you, Alex.
I thought this homework was pretty all right.
Okay. Other people?
I mean, it's all right. It's just tedious, and you can go wrong really easily.
Yes.
And one wrong mid-step is just a wrong answer as a whole. So.
Right, but you can still get partial credit if you make a mistake. So
yeah.
Just show your steps. What else?
I would say, I mean, it was the right amount. It's just that this particular week for me has been especially busy, and I had to push this back a bit. So it seemed like a lot, but it probably would have seemed like a lot if I had started it when it was first assigned.
Same. Yeah, I'm in the same boat.
Assignments come in waves, sort of. Seems like. Okay. Well, your next homework assignment, it has been posted and it's less problem. So hopefully it won't be too much. So let me know if you ever think too many problems are being assigned. What's up, Sean?
I'm sorry. I scanned the PDF of all my things on my phone, and I'm trying to email it to myself, and it's not going through for some reason. So I just want to let you know. As soon as it goes through, I'll turn it in, but it's
Okay.
for right now. It's just not. I don't know what's going on.
You got a new 6-axis precision motion system. Congratulations.
Thanks. I have such exciting notifications. All right. We're gonna have to move on. And we're going to look at that proof again from last time. Actually, we're gonna talk about a summary of what we talked about last time. So, last time we discussed random error. And we have this symbol here, delta x sub random, or random error, random uncertainties. And we can find our random uncertainties, x sub I for individual measurements, and delta x mean, the uncertainty of the mean, using standard deviation. So we talked about that last time. We can find the standard deviation, the sample standard deviation, which is the uncertainty in a single measured value x sub I. And then we can also find the standard deviation of the mean, which is equal to the uncertainty in the mean of all the x sub i's. So that was last time. And supposedly, I changed the slide. Supposedly it's true that, that last equation is true. And so this proof here intends to show that the standard deviation of the mean, when the mean is this, a sum of things divided by n things, the proof shows us that that uncertainty, if we propagate uncertainty, turns out to be the standard deviation of the mean as defined. So my slide last time was incomplete. I'm very sorry. It was not correct as written. So we have changed that here. So let's go through this again. To find an average, if we take a bunch of measurements x sub I, we can find the average x bar with this equation, 1 over n times the sum of all the x sub i's. And we can find the uncertainty in one x sub I by finding that standard deviation, sigma sub x. We're just going to call it that here. We're going to show the whole equation on this slide for sigma sub x. If we propagate the uncertainty for just the sum here, just the sum part, just the sigma from I equals 1 to n of x sub I, if we take that part here and take the uncertainty of that sum, that's going to be equal to, with our propagated uncertainties, the square root of n times the uncertainty in a single measurement squared, which is standard deviation squared, sample standard deviation squared. And basically that's because we multiply, we add all these up normally, these delta x sub i's, but since there are n of them, we just multiply n times that. So it's the same as adding them all up. Excuse me. Okay, and then so the standard, the uncertainty in the mean is going to be the uncertainty of the sum here divided by n, using our previous error propagation rules. So we take that sum, the uncertainty of that sum, we divide by n, and we get the square root of n, standard deviation squared over n, which we can simplify into the standard deviation, the sample standard deviation divided by the square root of n. So I apologize if that was confusing last time. Hopefully it is much more clear now. Questions or anything? before we keep going. Okay. Now here's another summary of what we talked about last time, just without the words. We can find the uncertainty in a single x sub I value, where the mean is the sum of those x sub i's divided by n, the number of points. And that uncertainty is going to be equal to the standard deviation, the sample standard deviation. And that equation is shown here. And then my uncertainty in my mean is going to be equal to the standard deviation of the mean, which is the sample standard deviation divided by the square root of number of measurements. Okay, now here is a quote from your book. This is from page 10. What is this? Sorry, page 101. Put that in. Page 101. And you can read all the text, but basically it's saying if we are doing this right here, if we're using this framework right here, if it's truly random, what we're talking about, then we can use this framework for our uncertainty in our measured values and our uncertainty in our mean. And if we do that, then 68% of our measurements will fall in the range of the true value plus or minus sigma sub x, the standard deviation. Okay, so if our sources of uncertainty are small and random, they really do have to be random. You can't have systematic error and this still be true. So we have to have removed all the systematic error for this to be true. If we only have random error, if something is literally like wiggling because of thermal motion, or we're measuring some other like thermal related agitation, like voltage noise, that's also truly random. If that's the case, and we're taking lots of data, then our results will be distributed around the true value of our measurement. And we will have 68% confidence that our measurements, future measurements, will fall in the range of the true value plus or minus the standard deviation, the sample standard deviation. Okay, I know you're thinking, why 68%? What is this random number? And we're going to learn that in chapter 5. So you just kind of have to take our word for it now. You can read ahead if you want. It's related to Gaussian curves and histograms. But that is the little bit of information that you need to be able to answer part B of number 1 from our measurement and standard deviation problems that we started last time. So I just want to show that answer. So as like kind of an example of this slide here. So I'm going to go to my PDF. Okay, we looked at this last time. And this is the solution for the problem that's listed on the As You Learn page. Where it says mean and standard deviation in class problems 216 and 218. So number 1 here we did last time in breakout rooms. And we talked about the solution, but we didn't really talk about part B. Estimate the probability that a single new measurement would fall within 0.02 seconds of the mean. How do we answer that? Well, that's related to this slide, or this concept, I should say, from your book. In that 68% of your measurements will fall in the range of a standard deviation around the true value, plus or minus. All right, so in this problem, we measured or calculated, excuse me, the standard deviation to be 0.01615 seconds, but keeping all the sig figs just for calculation purposes. And then I'm gonna spill over to the next page here. We were also asked to find the standard deviation of the mean, which turned out to be 0.005709 seconds. And when written as an uncertainty, that's going to have one sig fig, so 0.006 seconds. Now, part B, we are asked, estimate the probability that a single new measurement will fall within 0.02 seconds of the mean. Well, our standard deviation, our uncertainty for a single measurement is based on that standard deviation calculation. And if we convert that to an uncertainty, that's going to have one sig fig, which is 0.02 seconds. So that is coincidentally equal to this number they're asking us about. They're asking us, what's the probability that a new measurement would fall within the standard deviation? This is the standard deviation, 0.02 seconds. So I know since I'm using this framework that they have a 68% chance that a new measurement x sub I is going to fall within the standard deviation of within a range of one standard deviation around the mean, which is 0.02 seconds. So they asked that in, I think, probably the simplest possible way to, give you, to have like the simplest example. And we will explain that 68% next week, coming soon. Any questions about that part B or part A? Alrighty. We are going back to breakout rooms. I want you to try to do problem 2 and problem 3A, and then we will come back and discuss. So you should be able to get that Word document off of the As You Learn page to look at the problems, but I'll also put them up here while I'm doing breakout room stuff. So you can start working on those while I get this going. Hey people. Did any rooms finish number 2?
Yeah, we
finished.
Okay. Anybody want to volunteer to show their answers or tell their answers?
Yeah, I'll go.
Okay, thank you, Sean. I'm trying to
So
display the problem here. Go ahead.
Right. Okay. So For 2A, so we did the formula where it's standard deviation of the mean of X bar equals standard deviation of X over square root of N. So then it was
This one
three.
that I'm circling.
I'm sorry, your thing is really slow. Yeah.
Okay.
That equation, yeah.
Okay.
So then you're looking for uncertainty 3, so that's on the left side, and then 10 is on the numerator of the right side, and then you have square root of N. So then you just solve for N, and it turns out to be like 11.1. So we rounded up to 12. Yeah.
That's what I got as well.
Mhm.
Okay.
And then it's the same process for the second one.
All right. Anybody else? What did you have something to say, Abdel?
Oh no, we have the same working as well.
Okay. And Sean, what'd you say? The next part is,
It's 400. It's the same process.
yep, 400. Okay, that's what I got. Cool. All right. Can someone else volunteer to give an answer for 3A?
We have part of an answer, but we're not sure about the uncertainty part. But we have a answer.
Okay.
So the resistance we got was 2.425. And that's just done by averaging out all the resistances we
Yeah,
got.
and did you get those resistance values that are shown in my chart there?
Yep.
Okay.
And then we put the standard deviation as well, it was 0. I guess you can, yeah, we didn't, I don't know. Yeah, we have a different uncertainty. We didn't do that.
Is that a different answer from this?
Yes, I did, I guess what we did was I just took the difference between like the average and one of the bigger points, and then just put that as my actual uncertainty for a result, and then just divided that by 2, which is because it's like square root 4. Which like it would be like trying to follow the bottom equation.
Okay. So you were talking about the standard deviation of the mean.
Yep.
Oh, sorry, I was showing the sample standard deviation. Okay. So what was your final answer for the standard deviation of the mean?
Oh yeah, because like I didn't know how to get the actual standard deviation itself. Which all the square root stuff. What I got was like 0.0125, which isn't that far
Pretty
off.
close. Yeah. Okay.
Considering
So yeah, I
the
used the standard deviation definition equation here for the sample
Hmm.
standard deviation, and then found the standard deviation of the mean. And then I rounded to 1 sig fig. Anybody else get that same as me? Or maybe you didn't get that far yet. Okay. All right, so yeah, that was just practice for what we've already talked about last time. And then in part B, which I didn't tell you to do yet, but I want you to look at it now. I've written down the problem here. In part B, they ask us to use error propagation. Okay, so let's get to that point. We are told that the resistor is actually like the accepted value, the true value is 2.5 ohms for this resistor that we've measured 2.40 and 2.45 a couple times each. So our measured mean is 2.43 ohms, and our uncertainty is 0.02 ohms. And so the discrepancy, the difference between these two values, between our accepted known value, 2.5 ohms, and the measured value is significant, because this range, 0.2 ohms on either side, does not encompass that true value. Okay, so then the lab tech tells us there is a 2% expected systematic uncertainty from our measurement devices that we have not already taken into account. Now they tell us. So the question is to use error propagation to find the possible systematic uncertainty from that 2%, and then combine that 2% systematic uncertainty with the random uncertainty 0.02 ohms to get a total uncertainty. You're going to add those in quadrature. So square them, add them, take the square root to get a total uncertainty. And then you're going to compare your final value to the given value. Okay, so I want you to work on that, and we will talk about the solution next time. That is posted in the, as you know, on the As You Learn page. So we'll talk about 2B next time. All right. Just to display this for you, let me repeat that one more time. We showed this slide last time, but when you're considering both systematic uncertainties and random uncertainties, remember, up to this point in this presentation, we were talking only about random uncertainties, with the whole talking about standard deviation as the uncertainty. That is this random uncertainty contribution to the total uncertainty. If we also have some separate systematic uncertainty, then we combine those two in quadrature to find that total final uncertainty. So up to this point, we were talking about calculating random uncertainty. How do I know what my systematic uncertainty is? I have to compare my data points to each other, basically. I have to find the center of my measured, I have to find my measured value and see how far off it is from the true value to understand my systematic error after I've taken away or reduced the random error. And I do that most of the time with curve fitting. That's a really good tool to help me find that systematic error. But it's not just curve fitting, so I've said data analysis here. And one application of that is in that problem you're going to work on that we're going to talk about next time. 2B. 3B, sorry. On your own, you're going to work on that 3B, and then we'll talk about it next time. Now, we need to talk about counting experiments. We have a little bit more time to define uncertainty for counting experiments. So what do we mean by counting experiments? If we are literally counting a number of the same thing over and over, like number of radioactive events, the same thing's happening over and over, counting it. Or like at the bottom here, number of products detected by a detector on a conveyor belt. That's a counting experiment. Or number of eggs hatched in a week at a poultry farm, or I guess a egg farm, whatever that's these are, you're counting eggs. They're like all basically the same thing. So maybe some of them are a little bit bigger, some are small, a little bit smaller, a tiny bit different from the next, but you're counting them. Just to review radioactivity really quick for those who may not remember how that works. If you have an atom that has a nucleus whose number of protons is not equal to its number of neutrons, then there's an imbalance inside that nucleus. And that nucleus does not like that imbalance. It wants to have just about the same number of protons as it does neutrons in that nucleus. So if you have too many protons or if you have too many neutrons for some reason, however they got there in that nucleus is going to want to change to become more stable. Basically, it's unstable. And so the atom will give off energy, sometimes in the form of a photon, sometimes in the form of like a mass particle, a particle with mass. And then that nucleus like reconfigures and has a new number of neutrons and protons in it, more balanced, more equal. And that happens, there's a probability of that event occurring every so often, which is defined by the half-life of that material. And so for most of what we're going to be doing counting experiments for in physics, it's pretty much going to be for radioactivity. Of course, there's other fields that use counting experiments, but for the most part, that is going to involve counting radioactive emissions, or maybe like detection of muons or something from cosmic rays in the physics lab. All right, so when you have counting experiments going on, you really want to take a lot of data. It's not really, I mean, you always want to do that, but especially for counting experiments, you want to take a lot of data and then take the mean to find to help you with your reported value. Your reported uncertainty for your counting experiment is going to be the square root of your mean, of your average. And the next problem, the problem on the next slide is a demonstration that for a counting experiment, if you find the standard deviation, it's going to end up being the same thing as the square root. So we're still using uncertainty propagation, but it turns out that for a counting experiment, your square root is the same thing as your standard deviation. Okay, so here is number 6 from Taylor. I'm going to put you back in breakout rooms for a few minutes for y'all to work on this problem. Number 6 from Taylor. We have about 5 minutes left. So go back to your breakout rooms, at least get started on this problem. And then see you in a minute. Okay, everybody, did you get an answer for the mean?
We got 10.7 for the mean.
Me too. Cool. Standard deviation?
Working on that now.
Okay. I actually
got
didn't calculate it yet either.
3.27.
Go ahead, sorry.
3.27.
Okay, did anybody else get the standard deviation yet?
Yeah, I got it just by doing like square root. I didn't actually do the whole 20 term thing.
What'd you get?
3.27. I got that too.
Same thing, okay. Cool,
So
all right,
for the
well, we'll
homework-
show, go ahead, sorry.
Since this question's on the homework, do you want us to do like the 20 term sum thing?
Well, you just did it anyway for this class exercise, so you can just turn that in. Right?
Yeah.
Yeah, you have to do it
Yeah.
once, just once, Sean, just once.
Okay. It'll be kind of fun, I guess.
Yeah. You can, do something else while you're doing that.
Just mindless work. Yeah.
Okay, well, we have to stop. Thank you. That was fun. I'll miss you a lot over the weekend. Hope you have a good one.
Yeah, you have a good one too.
Thank you.
Bye, everybody.
Stay safe, everyone. Avoid the ice.
That's right. Be safe.
Have a nice weekend.
You too.
Thank you, Dr. Esther.
You're welcome.